And before start, I would like to ask our jurors to introduce themselves.
Okay. Hi. My name is Liu Wolong. I'm from Taiwan State.
My name is Lin Jianhong from Military Academy. Thank you.
Yudan from Korea Catholic University.
from University.
Thank you, Julie. Next, each team captain, please introduce yourself and your team members.
Hello everyone, we're Team Stanley and we're from Julie Junior High School. And my name is Curtis, and his name is Ray, and his name is Ken, and his name is Luke. And we're all 10th graders. Thank you.
Next.
Hello everyone, we are from Jingxing High School. I'm Chen Dingxiang. This is Xu Xianyao. This is Nambo Wang Zhijie. Thank you everyone.
Honorable judges and worthy competitors, I'm the team leader from Team Generation, and my name is Li Yiheng. This is Lin Shenzhe, Xie Haojun, Lin Yihui, Hong Weixi. Thank you.
As a reminder, please do not record this session or make any recording. That's the rule, okay? And next, we have 1 minute for the opponent to challenge the presenter for the problem.
Honorable judges and worthy opponents, we want to challenge you. Question 11. Balls on elastic band.
So set.
Thank you.
Okay. Please write down names on the whiteboard in Chinese, please, for each team. Okay. It's 5 minutes for the reporter to prepare. You want to read it? There's no note. You have no small points down. Is that what you mean? Yeah. Okay, that's fine. The reporter, please take the stage. You have 12 minutes.
So hello everyone, I'm a reporter from Typt Stanley, and today my topic is about ball on an electric band. First, this is a power scaler. Connect two metal balls with an electric band and twist the electric band and put up the balls on the table. The balls will begin to spin in one direction and in the other. Describe this phenomenon in electric and how the behavior of such a pendulum depends on level parameters. And we think the main focus is explain the phenomenon. And second, investigate how the behavior of a pendulum depends on the level parameters. And here's the table of contents. First, we'll introduce what's going on of the electric band and the ball. And second, we'll investigate the behavior of a pendulum. Three, we will talk about the relevant parameters of the experiment and the theory. Fourth, we will have a conclusion. And now the phenomena. This phenomenon is actually a transformation between the starting rotational energy to the electric energy. While transferring the electric band strength becomes the centrifugal force for the rotating motion, we can use the behavior of a pendulum to model it. Here's the experiment. And now, here's the behavior of a pendulum. These are the assumptions of the harmonic motion. First equation. From this assumption, we can know the relationship between periodic time position, tangential velocity, and the constant of the resulting force. The two is the case. And now we will introduce the damping into the equation. We assume the damping force is linearly proportional to an angular velocity, and the net torque equals to the resulting torque and damping force. Now we modify the differential equation will be written so that these sources are in opposite direction. We can also solve this differential equation for the under-damped case, where an omega dash is damped angular frequency, and the last one. And now, we can find the value of A and phi using the initial conditions. Then now we write out the function of T. And this shows the angular displacement is at any time T, if it's rotated by its initial angular solution. And on this chart, we can see the trend of the front half is going upwards, and that means the velocity is increasing. And on the left half, we can see that the velocity trend is going down. And I think the vibration is because of when we are doing the experiment, the balls, when we are gluing the balls and the electric band, there are some dry glue outside of the ball, so that touches the table, and that causes some vibrating and also some extra damping force. So the graph is not, and the data is like vibrating from the start to the end. And here's the experiment data of the torsional oscillation. And we try 4 times. And we try this in a way like we just strengthen the elastic band and a ball, and we turn it, and we will calculate the time when it's going the same direction and the other, and the periodic time is the time we measure. And through this equation, you can see we can calculate the torsional oscillation. And now we're going to talk about our conclusion. The factors of this experiment is the moment of inertia, and this depends on the diameter and the mass of the ball. Second is the damping and other resistance. This will consume the energy of the rotating motion and is not easily measured. For example, you can consider air resistance, or like from before we talk about the ball's dry glue will touch the table and cause it extra friction, and it's unpredictable. And this factor will also affect the radius of the rotating motion and max spinning speed, but not affecting the periodic time, because this is all related to the elasticity of the elastic band. And next, we will talk about the torsional constant. The lower the torsional constant, the faster the potential energy will be consumed by the resistor. Here is the torsional constant, and if this decreases, the angular frequency will decrease. And here is the total energy. The total energy will also decrease. And if the total energy decreases, you can see from that chart, the amplitude will begin to decrease, and at last, the elastic band will stop spinning. And here is the conclusion of our experiment process. The uneven elasticity of the band. This means that while we stretch the band, not every second the elasticity is the same, and the elastic band the elasticity might decay while we are doing the experiment. And second, the contact point of the band and the ball causes friction and unevenness of the ball. This means that before the experiment, we think that the glue will not hugely affect the experiment. But when we are trying out the experiment and when we got the data, this chart, and we found that it is a huge factor of the experiment, because it's quite a task for us to do the elastic band on the ball. And three, the dry glue might roll on the table, just like above. And four, the video might be recorded in a tilted angle. Here, you can see that when we are recording this video, the ball begins to move around on the table, and that's also because of the dry glue. And when this happens, we cannot just stay there and just still move our camera. So I think that will cause some issues for the data. And the theory flaws. I think there are a lot of kind of resistance to consider, but I think we can only model out the resistance of I think we can only model out the resistance of linearly, because other resistance we don't know how to calculate. And now the finding of the experiment. When we are trying out the experiment, the elastic band starts to curl up, and we didn't expect that. We only expect that it will just expand and get back together. And while the ball is consuming elastic energy, it seems to gain energy at the same time, because when it starts to spin, the rubber band from the sizes it shrinks, and that means the elastic energy is consumed. But when it shrinks, it starts to rotate, and I think the rotation will cause some extra energy to be created. And for the future outlook of this experiment, next time I think we can try to do this experiment with a more formal equipment and also the recording devices. And this book can be more accurate. And second, we will investigate more about the gaining energy while the ball rolls. And this refers to the second point above. Thank you for listening.
The opponent, you have 2 minutes to ask questions.
Honorable judges and fellow competitors, I'm the opponent from Team Detonation. My first question is, have you considered the linear motion on the radial axis?
Linear motion.
On the radial axis?
No.
No. Okay. Have you considered friction into your experiments?
Yes. But
Can you
we don't
elaborate on that?
but we didn't know how to model it.
Okay. Have you calculated the theoretical time period of the cycle?
We try to do it, but in the data you can see that the periodic time is uneven and it didn't show the lot of things. You know, we cannot define that which is the start, which is the end. Like you can see, the start is like
Okay. Can you go back to the page where you talk about the differential equations? Yes. Can you define what is your damping from?
Oh, the damping. Oh, because we think a lot of kind of damping is linear. Because we did some research about the damping, and we think that a lot of damping is linearly proportional to the velocity.
Okay, I understand. Can you define theta?
Theta?
Yes. What is theta?
It's a position of the ball.
Do you mean when the ball is spinning or
Yes.
the ball's own rotation?
Spinning around.
Okay, I understand. And how do you calculate your moment of inertia?
I think we forgot.
Okay, we
but
have to stop here.
Okay,
I'm
thank you.
sorry. 3 minutes preparation time for the opponent. The opponent has maximum 4 minutes to present his work, and followed by a total of 14 minutes discussion with the presenter.
Honorable judges and fellow competitors, the opponent from Team Detonation. And today I'll be opposing problem 11 for elastic band. So first will be the problem statement. Connect two metal balls with an elastic band and twist the elastic band and put the balls on the table. The balls will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on the relevant parameters. So the main focus on this problem should be to explain the phenomena and consider the different parameters. So this will be our outline. So first, for the reporters' theory experiments, the phenomenon they explain as a transformation between the rotational energy to elastic energy. And the balls will begin to spin in one direction and in the other. The theory using harmonic motion, damping force, twisting, but they didn't quite consider the radial linear motion, and they model it using a differential equation of a damped system. And their experiment, they do 4 times of the experiment for torsional oscillation in different inertia environment. And their conclusion is that the vibration and the damping force cause the vibration of the data, which is their error moment, and their moment of inertia diameter mass influence the results. The damping and other resistance make it unpredictable, and the factors don't influence the time period. And the torsion, as torsion constants lower, the resistance takes more potential energy, but I think there's something more about this we will talk about later. And their improvements that the uneven elasticity and the contact point of the band and the ball and the twisting of the own elastic band, the dry glue and the tilted angle of the camera. So here are their pros and cons. They observe the phenomenon from the video and they give clear graphics to demonstrate his theory about the damping and the differential equations. They put forward potential flaws in the theory and experiments. They identify the correct key questions of the problem. But for their cons, they failed to show video phenomenon at the beginning. They only showed it maybe way too late. And they didn't show the number of the pages. They failed to explain the formula of phenomenon clearly. They failed to analyze the meaning of the data precisely. And the lack of concrete evidence to support the theory. They lack of other parameters, and they fail to measure the moment of inertia. And they ignore factors like friction that do not only cause marginal differences. So our discussion will mainly be on these few parts. First, for the experiment, is the friction and the linear motion, the time period, and their scientific data. And for our theory, we'll be mainly focusing on the twisting of the elastic band, the damping of the system, and the radial linear motion. And now I would like to start my discussion. Please.
So first, can you talk about your...
Sorry, I think I should be asking the questions.
Okay.
Can you tell me what exactly is inside of the damping, that damping constant?
Oh, you mean?
I mean, what resistance force do you think is that we can model it into damping?
I think, all the resistance. We think because the table's surface is unevenly buffed, so I think that is also a consideration for the resistance force and
Okay, I see. Thank you.
yeah.
Can you explain again how do you measure the how do you think you can measure the moment of inertia from the system?
So we look up a formula on the internet, and it says that when a ball is spinning, the moment inertia is 2/3 times m and the radius squared.
2/3. So you're assuming that your balls are hollow. Is that correct?
No.
No, they're solid.
Yeah.
Okay. Now use the backboard. So first I want to talk about the theta in your theory. So this is all in the elastic band. So you mean that when theta is when this turns this angle?
Yeah.
Is that correct?
Yes.
Okay. But in your differential equations, you write it down as the second derivative of theta and plus this is your theory. Is that correct?
Yeah, I think mine.
Okay. No, well, the minus should be on the other side. Since damping. Okay, it's fine. I want to talk a little bit more about your definition of theta. Since the twisting of kappa, is it, where is it? Where exactly is it twisted? Yes, yes, yes. So if we, the elastic band is connected with 2 bolts. So if we look at a radial side, we can see that this is the elastic band, and just imagine that it comes down, right? So the twisting should be this direction, or maybe in another direction. Is that correct?
Yes.
So,
But when I don't know how you see it in the demonstration video. The elastic band starts to curl up like
yes.
this.
Okay, let's first talk about the ideal condition, that if the elastic band didn't curl up. So the twisting should be on this direction, or maybe on the other direction. Is that correct?
Yes.
So how do you relate, since the kappa is about this rotation, how do you relate it with the rotation of the ion balls? Are they the same?
Yeah, I think we can make some correction from.
Okay.
Yes.
And next about the damping, what do you think? Can you explain again what you think is inside of the damping?
Start rotating.
Yeah.
When it starts to rotate, it has a force here. And also there might be some colliding between the blue and the
Okay.
yes. And okay, so what do you want to ask more?
Because first that's
This when we are doing the experiment, we think that a lot of the damping is unpredictable, and when we are trying out different types, and the result will be different. Sometimes the glue randomly touches the table, and sometimes it just touches the table all the time. It starts to run.
okay. So but how can you make sure that is proportional to the first?
That's just an assumption.
Okay.
Yeah.
Do you think that the twisting of the elastic band will cause damping?
Cause damping.
Yeah.
Yes. Yes.
Inside of the
It will. I think I didn't mention it in our conclusion, right? So there's a mistake. I think I should talk about it.
Okay. Another question. How about friction? Do you think friction is, we can ignore friction, or can we not?
I think sometimes we can, or sometimes we not. But in our experiment, we put it on the wooden table, so I think the friction is quite a big factor for it. But because this is a model, we will try out a model on for the ball, and if we are on a glass table, I think the friction will be a little bit less of a factor for this experiment.
Okay. For the friction, where do you think that friction? Can you draw the direction of the friction?
If the ball turns here, turns like this, the friction will open out.
Okay, but how about the linear? Will there be friction?
Linear side, I think the friction will be when it starts to untwist.
Oh.
You know what I'm saying? Untwist.
Yes.
And the ball, for this example, if the ball is untwisted, if it untwisted in this way, I think the unevenness of the okay, I'll draw it this way. If this is an elastic band
yes.
from this, you can see if this starts to twist, this might be some uneven edges for the elastic band. So I think this causes the other way. For the
Oh, okay, okay. how do you think that when you're twisting the elastic band, it contracts?
Yes.
Yeah. So you release it and then it spins around and expands.
I think it goes to the original state.
Yeah. But it does move outwards and inwards, right?
Yes.
Do you think that the friction between? But how do you think that this movement affects the system?
This movement.
Yeah.
I think when it opens up the I think the moment of inertia will change.
Moment of inertia will change.
Because the whole system and the radius will become greater, and the whole system, the moment of inertia will change again.
Okay, so can you define the moment of inertia again?
We are calculating and because why is for the two of the balls.
Okay, so why do you think it will change when when the elastic band expands?
Because the R.
The R. So what is the R exactly?
I'm sorry. This R is the radius of the ball.
Okay. So do you think that when the ball expands, the friction on the side will affect the whole system? Yeah, when it's like
you mean the
moving outwards,
friction?
there should be friction that's going inwards, right?
Oh yes. That will definitely be friction for this system.
Okay, so how do you think it will affect your formula? Or is it also considered in the damping?
I think it's considered the same.
Okay. But from my perspective, the ball is spinning on this side, this direction. But for us, if we look at this picture, if this ball is going inwards, the friction should be going outwards, right?
So can you refer this picture to this?
Okay. So this picture is we view it from this perspective, and if the ball is going, the ball is going outwards, the friction should be going
inwards.
Inwards.
It will be inwards and outwards.
Yes. So, but the rotation, the direction of the angular velocity is actually also pointing on the radial side. So how would friction affect this rotation, this friction?
Oh, so first, I think when you mean this rotation, I think they will not be related because this rotation is all about elastic band.
Okay.
The twisting of the elastic.
How about the time period? How do you define a whole one cycle or a whole time period?
I think it goes around in one cycle. I mean that's one time period for the.
So you see the okay. First, let's clarify. I think the theta you're relating with kappa, it should be this rotation.
Oh yes.
Yes. So if we want to complete a full cycle, shouldn't it just be when it goes back to its original state? Right. So maybe the time period should be when it spins outwards, inwards, and then this is on the maximum of the negative.
Maximum,
and it should go back again. And
I think they should be considered in the kappa because we only consider the twisting. We didn't consider the expanding or.
Okay.
Yeah.
Do you think that kappa will affect the damping? Because that was mentioned in the theory. Yes.
Okay, your time is up. 1 minute for your opponent to summarize.
Okay, for the discussion, we first talk about the differential equation they mentioned. They missed out quite a lot of. They're talking pretty. They have a lot of ambiguity inside of the damping system, and they might have a wrong understanding about how theta is defined. And for the motion parts, they didn't consider the contracting and expanding inside of the system. And they might also have a wrong insight about how time period is defined through this type of equation. And about the kappa is the torsion constant, so it's related to theta. Oh, sorry, I didn't write it on there. But it shouldn't be one of the factors that affect the damping system. Thank you.
3 minutes for the reviewer.
Okay, first, before that, I would like to ask, so can you turn to the velocity graph?
You mean the data page?
Yes, I'd like to ask, it's okay, I will just ask. Why is your graph have different kind of statement about denting? Like in front of your graph, the denting is like only dent for a little bit, but at the back it has falls for a large distance.
You mean to start this one?
Yes,
From which segment can you
like from 2.5, and
okay, alright.
it drops for a large distance.
I think this because there's a hole on the table. It will like stops a lot. There will be a unpredictable friction for the ball.
Okay, got it, thank you. To the opponent, do you think friction will affect the denting and the rotation?
Yes, I do think so. Actually, I think that the friction have two types of friction. First off is the sliding friction on the radial side, and the other is the rotational resistance on the outward, which is tangential to the which is parallel to the movement of the balls. So I think that rolling resistance will affect the denting system.
Okay, thank you. And which is the major effect of it?
You mean a major effect of what?
Oh, sorry. The effect of damping about rotation.
About damping to the rotation? I think the damping will mostly affect how we determine the time period.
Okay, thank you. Now, to the reporter, why is your, we've seen your graph, what, you have mentioned that energy will increase instead of decay. But
you mean in the conclusion?
yes.
Okay. Yes. The second part of the part, experiment finding. You mean? Okay.
Where does it gain energy?
It's because when the ball contract together, when the lens being constrained in length, it will also rotate. It rotates at the same time, so it will turn like this. And the torsional energy will start to be gained. The torsional energy of the lens will gain.
Well, about your function, your energy should decay. Can you explain about that?
Can you repeat your question again?
And your function page, your energy should be decayed. Can you explain about that?
Energy will be gained. And the rotational frequency will decrease because of tension.
Okay, time is up.
Thank you.
2 minutes preparation time for the reviewer. Okay. Okay, review has 1 minute.
Okay. Hello everyone. I'm the reviewer of Team Tosi, and we're going to talk about ball on the elastic band. Okay. Of the overview of the reporter's presentation, the theory is stemming force causes the decaying of the energy. And they tried 4 times and turned the elastic band and observed it. And the conclusion, the damping will affect the motion, and there are unpredictable friction to the result. And when the kappa is larger, the faster the kinetic energy will decay. And this is the problem statement. About the strength of the reporter, they have focused on definition on the damping theory and tell us about why the chart is strange. And the areas of their improvement, their demonstration video can be more complete. And their experience things didn't fit the theory. And they have a lack of experiment, not enough, and their experience is not accurate enough. And they should have page numbers and talk more about the kinetic energy decay. And about the component, they ask experimental questions. Show understand to the public and tells the improvement to the experience. And the areas of their improvement, they will sometimes interpret the reporter as speaking. About this discussion, the point based on the opponent is what exactly is in the damping constant. And the reporter table will provide the damping. And in our opinion, it is just the ball and the band doing the damping force. And how to relate K to a ball rotation? The reporter response is that K will affect the rotation. And twisting of the band will cause damping. The reporter response is yes. And we do think the twisting of the band will cause damping too. And about the point raised by the opponent, can we ignore friction? The reporter response is, it is a big factor while the computation isn't controlled. If the table is smooth enough, the effect will be smaller. And in our opinion, yes, the table will provide a big friction to the experiment. Reducing the band and the ball will affect the friction between the ball and the band will affect more. And the point raised by the opponent, the movement will go inward and outward. And the reporter response is that the moment of interior will change since then. In our opinion, we agree with the reporter's response. And this is our question. To the opponent, how do you think exactly that friction might affect the rotation? And the opponent says sliding friction and rolling resistance will affect. And our next question is to the reporter, why the velocity will drop a lot in their experimental graph. And the answer from the reporter is, there are some unpredictable holes on the table, and yes, maybe that is a little bit of problem in their experience. And the next point is they have lack of explaining their experimental setup. And next, the reporter didn't mention enough of energy decay. And they did a less different parameter, and they didn't clearly define the period. And maybe they should tell more about the experimental environment and how the friction affect minor to the damping. And this is our presentation.
2 minutes for concluding remarks from the reporter.
Okay, so first, thank you for your listening, and I think we should improve in a lot of ways. First, the experiment, and second, the theory. Because we didn't get enough research from the theory and all about the energy decay and all the equations that we list, and I didn't make a clear definition of every equation. So I think that is a big part that we should improve. And second, the experiment environment. The reporter mentioned about the holes on our table. That causes a lot of friction. I think next time, if we have enough money, we can buy a flatter table and try different materials of the table and see and consider the friction coefficient of the table. And thank you for
Okay. Questions from Joyce?
The report, could you show the data? Okay. What is the velocity? And how does it relate to the parameter that you are using in your experiment?
Oh, I think the velocity is the actual velocity of the ball moving on the table. This velocity is not about the spinning. It's about the actual movement of the ball. We use tracker to track every picture, or because we cut the video in a lot of pages or pictures, and we check every picture's velocity, every picture the ball's velocity. And this, you mean this connected to what?
How does it connect to relate to your parameter?
This related. Oh, because the parameter is related to is the kappa, and that affects the omega, and omega also affects the speed because it is a rotating motion, right?
So that's the linear velocity.
Yes.
Of the ball.
Yeah. So we are trying to track the how fast the ball moves, because it's in this system it's an energy transformation, right? So I think if we track the velocity of a ball, we can find how big is the energy of the system.
The question is, you have theta here. Theta is the rotational angle, right?
Yes.
And that's linear motion,
Yes, that's
linear
linear
velocity.
motion.
How do you relate these two?
So we try to use a formula from circular motion. Circular motion to change theta into the velocity.
Since you have experimental data and theoretical model, do you have any fitting or any compare between these two, particularly your data and the model?
Because when we are,
any
no, we didn't, we tried to do that, but and finally we didn't do it because
you fail, right?
Yeah, we failed because
Okay.
there's too much inconsistency. Yes.
Did you consider motion along the rubber band?
We try to consider that because the friction,
The equation doesn't have it.
Huh?
Does the equation have that motion?
Only the rotation.
So you didn't consider
Only the
this?
like rotating too fast and
Yes,
slow.
I know, but you didn't
We
consider
didn't
the
consider
contraction or
Yeah,
extension.
yeah.
Did you change a different rubber band? In other words, did you try a different?
Different rubber band?
Yes.
Oh, no, because the rubber band we use is the best result for gluing it onto the
Yes,
on the ball.
I
And that's a
understand
great
that.
test for us. We did that for.
Say, if we change the elasticity of the rubber band,
Yes, I think next time we can use a thicker one or a more uneven. I think we can find a like rubber band shaped like a hole, like in the
Okay.
cylinder. Yes. And
if
not
we
not
change
the square one.
a different rubber band with a different elasticity,
Oh.
elastic constant, what will you expect?
Oh, I think if it has a greater constant, the velocity will decay faster. It will the peak will be at the front of the data, right? If it
Okay.
has a greater.
Opponent,
Yes.
What do you think about my question?
I think the elasticity is related to the kappa value, and the kappa value will be part of the determination of how the time period will be.
So if we increase the elastic constant, will it spin faster or slower?
I think that since using their formula, I think it is reasonable to simplify it into a damping motion. So using their formula, the time period should be 2 pi and over the angular frequency, which angular frequency should be related to the kappa value, positively related to the kappa value. So if the kappa value increased, the time period should decrease.
Do you agree with you?
And in my opinion, when kappa increases, I think the velocity will also increase a bit.
Okay. Any more questions from Jules? Thank you.
Thank you.
Recording scores. Okay, let's show the scores for the reporter. 5, 4, 6, 6, and 5. Opponent. Eight, 6, 8, 8, and 7. Reviewer. 6, 6, 7, 8, and 6. Let's conclude this part. Let's take a 10 minutes break. So we will convene in 10 minutes at 9:35, 36. Okay, so change your seats before you leave. Probably that will save some time.
You a model? You put model in put model united. That's why we most of them feel like honorable.
Oh, well,
judges.
say the tradition.
Yeah, like that's really a model administration. You model United Nations.
Yeah, it's just a basic courtesy.
Yeah, just read.
It's true.
对，report 到上 report， 然后到我们昨天不有讲，所以我们等一下会。
第二队、二队，全部就是912，全部过，全每个都要过，有2块都过了。过了，这是实验的第二队912，里面只有912部分912全部过，另外一半你们家打他们，
反正他们都在比决赛，
他们那种比加拿大打过，就是过完，对的，没有，就是另外一个。文心开始有开始，文心平时开始用排队，没有吗？哎呦，不会换马甲，马甲。在 A 用。哦。那你要 start 可以放在哪里？
然后不可能太 casual，因为
我们今天有穿短袖吗？过分了，他就这样子老走。
200多了。
那你这个最强的就拿我，没来那个。 原来那个英国机器，Xbox 是不是？
那种是事业最强。
原本是被异想 C 者，昨天问的问题，
他说没来，没来干嘛？他是看全部做报告。没有啊，他平常有做什么没有？
有啊，平常有做什么？我的，你说做哦，
哇，可以啊。
但他喜欢跳。
有啊，是这样，他不来没他。
上个礼拜我们还弄实验数据啊，他们还没缺过，差不多。
他的程度跟我们中间很大吧？我们跟他对错对。
我们没有对吧？这是算最好的，try our best。
他每个可，
我没得选啊，班上没人理我，你知道吗？
你们一个班啊？
我们快报全报一个班。
很啊。
别班更可怕，你知道吗？对啊，别班都在跳热舞、打棒球啊，我不知道在干嘛。
然后偷嘴其他人，他就被屌。
但是那也没办法。谢谢。之后我们班还有一个人跟实验，然后是国际化奥运，够屌吧？国际化，然后呢，他每天跳舞，
他每天跳舞，不知道在干嘛。
干你娘，说要跳舞去啊？
那作业还要抄我，你知道吗？
国际化奥运，跳保送，
哦，你们一定保送。
我怎么电工大学的？
化学人才都去电电，
很有病。
电力系可以找到各种老师来，补习班老师，然后还有补习班老师啊，还有补习班老师来，语文课，还有补习班老师。台大电机是不是可以找到补习班老师？
不要用这个来。
等下抄那个。
谁借我一台 laptop？
你们的电脑来自
谁借我一台啊？借我一台 laptop。
缺电脑。
我拿一定要不要？
1秒钟吗？1秒钟的东西。跟我差不多了，不会啊。
你现在有人帮我做题，自己帮我做题。对你，我讲过 front house。
我问一下你们 review 是这样狂抄，
就是从头到尾，
他们问题就一定要打下来，一定要抄他们。
不一定，我没有打那么多。
没有，我说过程问题，他丢给我问题，你们就打。
不会全抄，不会全抄。抄部分重要的题点的全都有，没有什么就是什么。
直接上去。
生活费很爽，只要学好，就只要3讲，然后这样可以做一个。正常的电路，
换上，
然后电子，水化学、物理，
但是没有画奥运。
按你包出什么？
没有，我是领先，或者是比赛。
他不去考不好。
哦，
我是在看动漫。
哦，
哦，我们休息15分钟啊，好吧，15分钟，15分钟也 OK。叫他回来我们就开始，没有回来我们就继续休息。I guess everybody's here. No. One person is right? Well, here, right? Okay. We can start our second session for this morning. And opponent has 1 minute to propose a question for the reporter.
We want to challenge number the three-sided dice.
Three-sided dice, that will be number what? Number seven. Okay, number 7. Reporter number 7. Three-sided dice.
Yes, we accept.
Number 7 is not available.
Yes, we accept.
No, you can't. You don't have number 7 there.
Oh, I believe this is not our.
Oh.
That would be the yes.
Let me check. Look, number 7 is not allowed for the reporter, right? Is it number 7 for the three-sided dice? Okay, but the table shows number 7 is excluded for your team. Am I right?
You haven't reported or proposed it yet.
要查一下，他们说他们没有 report。哦，Okay, the opponent was presented number 7 by you, right? Yesterday. Okay. No, then it's excluded from you. Okay, let's restart. You have one minute to consider your question. So the opponent has used number 7. That's why it is excluded.
I want to challenge number 15 for economic side.
Number 15. 1 minute for the reporter to consider. Reject. So the opponent has another 1 minute to propose another question.
Number 2, relay disk.
Relay disk number 2. 1 minute for the reporter to consider.
Relay disk. Just review.
We reject.
Reject again. So another minute to consider the problem.
Number 8, equipotential line.
Equipotential lines number 8.
Give me a second.
Okay. Number 8 for this session. Please write down names for each team for this problem. Okay. The reporter has 12 minutes to present his work.
Okay. Honorable judges and worthy opponents, I'm the reporter from Team Detonation. Today I'm here to present problem 8, equipotential lines. And this is our outline for today's presentation. So from the problem statement, we'll do experiments to observe the phenomenon. And after we see the equipotential lines that we draw, we can come up with our own theory of the equipotential lines. And we'll do experiment to verify or to correct our theory. And last, we'll come to our summary and conclusion. So first, this is the problem statement. So it says, place 2 electrodes in a container of water and apply a safe voltage to them. Using a voltmeter, determine the electrical potential at various points in the liquid. Explore how the found equipotential surfaces correspond to the possible assumptions for different experimental conditions and for different liquids. So we believe the focus today will have 3 points. The first one is to predict the shape of the equipotential lines. And the second is to observe the equipotential lines under different parameters. And for the third one, it's explaining the difference between the real condition and the theoretical condition. As you can see in the picture, this is the measurement of the voltage that we draw on a paper. So this is our theory. For our theory, the first one, when the circuit is triggered, then transfer of the electrons will create electric fields. The charged particles of the external electric field are subjected to the force exerted by the electric field. And the potential is the electric energy possessed by a unit charge. So you can see, here we imagine electrode as long conducting wires, so we can do the calculation. This is a calculation for the electric field and the voltage, electric voltage. And because the electric voltage is the integration of the electric field, we can write the following formula. And after calculation, and at every point, we have to calculate the plus the voltage difference between one point to the negative and the one point to the positive, so that we can get the voltage between a voltage of the point. And that is our calculation. And here we want to emphasize a point. Here we add a correction in the formula because by the definition of the electric voltage, it has to comes from the positive side to 0. So if we just draw the graph without the correction, then it turns out that the negative part, for example, in our experiment, the voltage difference is 6, then it will turn out to be -3, which is not the definition of the electric voltage. So we add a correction. You can see this is our prediction of the shape of equipotential lines. So according to our formula in the theory, last page, since there are x squared and y squared in our formula, we assume that the shape of the equipotential line should be logarithmic, and the x-axis and the y-axis should both be its axis of symmetry. So you can see in the picture, this is the prediction of our shape for the equipotential lines. And on your left-hand side, this is a 3D model for the equipotential lines. Now come on to our experiment. To accomplish our experiment, we need the following equipments. First, we use the digital multimeter to measure the voltage at different points. And second, we use the weights as our electrodes on the negative side and the positive side with a distance of 14 centimeter. And we also use the dish and add water and some solute in it to conduct the different parameters influence the result. And we want to emphasize that the water is shallow so that the interference will be low. And this is the graph paper we plot dot on it so that we can measure, we make sure every dot has a distance of 1 centimeter so that it has equidistant. And here we use water and potassium chloride and sodium chloride for our experiment. Also, we use lab power supply to create voltage. And here's our overall experimental setup. So after obtaining the potential data from the experiment, we run them through a MATLAB function used to estimate contours in geography, and thus obtaining the equipotential lines of our experiment. So here's our first parameter. We want to explore how different potential differences will influence the outcome of our equipotential lines. So as you can see in the picture, when the voltage is higher, the equipotential line is denser. and we'll explain later. And also we can see that the second conclusion for this graph is that despite different electric potential, the shape of the equipotential lines looks almost similar. Okay, here's an analysis for this experiment. According to the formula in our theory, since the same kind of solution will have the same boundary condition, therefore the results will look similar. However, since the initial voltage is different, the phi here, phi value, which is the voltage between the positive and negative, will be different. And also because when the voltage is bigger, because in our graph, each line has the same gap of the voltage. So it will become denser if the voltage is higher. Here's our second experiment. We want to discover how different types of electrolyte will influence the result of the equipotential lines. So you can see in our experiment, we used the water and potassium chloride and sodium chloride to do the experiment. And we maintained the voltage at 6 volts. So from the experiment, when the solution is different, the shape of the equipotential lines looks really different, as you can see in the picture. Okay. For this experiment, here's our analysis. Different solution has different boundary conditions. Thus, the distribution of the electric potential will be different, which leads to the different density of the equipotential lines. Now, moving on to one of the topics that the problem requires us to do, which is the difference between the real condition and the theoretical condition. So here's the difference we found, and we will explain it and elaborate on it later, respectively. So the first one is, why is the equipotential line around the electrode a diamond shape? So our explanation for this is that the equipotential line around the electrode is not round because of how the lines are being plotted. In our cases, we use the contour function of MATLAB. And second difference is, why do the equipotential line curve toward the electrodes? So our explanation for the difference is that when experimenting with soluble salts, the equipotential lines curve toward the electrodes at certain regions because the associated anions and cations flows toward the opposite electrodes following the electric field lines, making the potential rises or decreases along the line. And here's our third difference discovered in the experiment. And why are the equipotential lines denser around the negative electrode and looser around the positive electrode? There are several explanations for this. And first we come up with an explanation is the sequence of our experiment. So in our experiment, we first start to measure the voltage of the liquid from the negative side to the positive side. So it may, because of the time sequence that causes the difference of the negative electrode and the positive electrode. And to solve the problem and to ensure if this is the major factor, we do the experiment from the positive side to the negative side to see if the results will differ. And it turns out that it turned out to be the same. Therefore, we factored this assumption out of our experiment. And this is another assumptions for the question. So take potassium chloride, for example. When an external voltage is applied, potassium ion flows toward the negative electrode, and the chloride ion flows toward the positive electrode. Well, chloride ion can get rid of its electron without issue. The potassium ion will not come out as a metal, but rather from hydrogen gas at the negative electrode due to the reduction potential difference between potassium and hydrogen. The result of this is that the two ions builds up around the negative electrode and reduces the solution's resistance in that region, making the equipotential line denser. Okay, here's our conclusions and summaries for this experiment. So we come up with the following conclusions. The first one is the ideal equipotential lines correspond to a logarithmic function according to our calculation for the theoretical equipotential lines. And for the second one, same liquid have similar equipotential lines, but the initial voltage will affect the density of the lines, which I just explained it before. And for the third, the epsilon varies from different solution, and this value is in our calculation. Therefore, the equipotential lines will be different from each other when we have different solution, different liquids. And here's our references for the experiment. Thank you for listening. This is the end of my report.
Okay, now the opponent has 2 minutes to pose questions.
Okay, so I have some questions to your experimental setup. Does your needle, you use needle to measure the voltage?
We do not use needle for. Here we can see from our equipment, and we use digital multimeter to measure the voltage in it.
So, yeah, I
It's
mean
not probe.
the need of the digital multimeter. Did you put it in the water, on the surface or in the middle of the water or to the deep?
I put it on the bottom of the water.
On the bottom?
Yes.
Okay. So, and do you guys do you do different concentration on the KCl and NaCl?
We believe that will affect the experiment because the ions in it is different. However, maybe will improve it later in the future.
Okay, so that's the end of my question.
Thank you.
3 minute preparation time for the opponent. Okay, your opponent takes the floor. You have 4 minutes maximum to ask questions, then another 10 minutes. total 40 minutes.
Good morning. Today I'm the opponent of the potential lines, and I'm the member from TOSI. Okay, so this is a problem statement. So the main focus is the expectations and realities in different conditions and liquids, and might also need some prediction because of the expectation. Okay, so this is their structure of solving problems. For observation, they measure the voltage, and in theory, they did calculations of the electric field and the voltage, including corrections, which is really well done. And experimental setup, they estimate counters in geography. And for data analysis, they use different potential, they have different potential and different types of electrodes. So in their conclusion, they say that initial voltage will affect the density of the lines. So this is the pros and cons for the reporter. So to the pros, they have the clear formula, which is the clear deviation, and they have derivation, and they have clear experimental setup and sufficient data to support their theory that they have used the correct one. And to the cons, the lack of explaining how the graphs are different, and they can maybe try more types of materials and concentrates. Okay. So to the discussion, we will want to talk about the electrolysis and how will a different liquid affect the result and the main parameters to the experiment. And we'll discuss about the different concentration about the different solids. So let's begin on our discussion.
Okay.
So the first question is that can you turn to the page 3?
Here's page 3.
So how do you draw the voltage on the paper?
Okay, so on the picture you can see there's an X here and X here. That's the negative electrode and this is the positive electrode. So we use a weight here and we point one side of the we point one side here and probe the other side into the points we dot on the paper. So we get our numbers for the voltage at different points.
Okay. And how would your time, like pointing a point on the grid paper, how will your experiment last?
I believe the time span will in fact influence. So we do our best to minimize the time we do, and for each experiment we do it within 10 minutes.
Okay, so.
And also we want to clarify a point is that the time span will affect, it's because the concentration or because of the electrolysis or the ions in it become solid or become gas. So in our experiment, we all use saturated liquids so that the concentration will not be influenced. So we can mitigate the influence of the time span.
Okay, got it. So do you observe the bubbles in the water, or do you have when you are doing the experiment, do you have some bubbles in your tube or something?
In fact, there's barely bubbles in it because we move under the wire. So now we can mitigate and minimize the infection of the influence from the bubbles you said that may be made.
Okay, I got it. So when the electrode is when the needle is putting into the water, they might have some electrolysis. So how can you prevent this from happening?
So as I previously stated, In our liquid, we use saturated liquid, so the concentration will not be influenced by the electrolysis. In this way, we can minimize the influence of your problem.
Okay, so let's move to the page number 8.
Here's the.
So as I see in the chart, you said that their equipotential line is similar because it is water.
Yes, because the liquid we use here is water, and the difference is caused by the different voltage.
Okay, so can you explain why you use the left of the left graph? Why is positive electrode is bigger than the others? Because you said that if it is water, their lines will be similar.
Yes.
So why will this become different, like bigger than others?
Are you I see a question about why the equipotential line of the water in 3 volts is not as dense as the others?
Yes, because I see this part and this part of the equipotential line, and this part is like there are some difference between them.
Our explanation for the phenomenon is that the water we use is tap water, so there might be some ions in it that influence the result of the equipotential lines. But from the big part, it looks similarly, and compared to the other experiment, we can say that it actually looks similar in this condition. So our explanation is we use tap water, and maybe we can use pure water in the future to improve the experiment.
So is it correspond to the resistance or something else? Because of
resistance?
your water resistance, the part of this, the part showing this place larger, right? Because of the difference of the resistance.
I believe that might be a possibility, and as I stated, our explanation is the possible ions in tap water, and that will be our improvement in the future.
Okay, so you said that you didn't control the water, the same water, because
we control the same water, and because in the water they all have ions, and if we have bigger voltage, it will become denser. So reasonably, this will be denser than that. And I want to explain about the difference between the positive side and negative side, and it's because of the ion in the water.
So you haven't tried to use the distilled water to do this experiment for the measuring the
water?
Distilled.
Okay. Because the liquid you said cannot can barely create a current inside the liquid, so that might not be a possibility that can be done.
Okay, I got it. So, will the temperature affect your results, or did you control when your experiment environment, or?
Yeah, we control our experiment in our environment in 25 degrees.
So do you think that the temperature will affect your result if you didn't control it?
Actually, I did. And if you're asking me if the temperature is the parameter I will set, I don't think that will influence the result.
Okay, so let's move on to the page number 10. Okay, so can you explain more about why the equipotential lines at the negative electrode will be have more density?
Density?
Yes.
Okay, so because of the ions, and For example, take the potassium chloride, and in the liquid, there's potassium ion, and it will go to the negative side. However, it will become denser. However, on the positive side, there's the chloride, and that will become a gas and get out of liquid. So the equipotential line will not be as dense as the negative side.
So, how about do you think that the solid, the electric negativity of the solid will affect your result?
You mean the solid from
your this experiment, like your KCl and NaC?
I think that might be a possibility. And to improve this, we can take out of the solid that created in the liquid for the more accuracy of the equipotential lines.
So why do you choose the KCl and NaCl to do the experiment?
Can you rephrase?
So is there any reasons that make you choose the KCl and NaCl to do this experiment?
So we first take the potassium chloride for example, because the ion mass is nearly the same, so that we can control the maybe possible different velocity between the movement of the ion. So that's the reason why we choose potassium chloride. And for sodium chloride, we can compare it with potassium chloride to see if the velocity will differ, and it turns out to not influence the result a lot.
Okay. So let's move on to page 4.
Okay.
And can you explain your formula, your V and your formula?
The V is the electro voltage.
Electro voltage. So it's what you measured, or?
Can I write it? Can I do it on the blackboard? Thank you. So in our experiment, we draw the dots on the graph, and as you can see here. So this is the negative electrode, and this is the positive electrode. So that is the calculation for example, we take this point, which is maybe the xy, and for the positive electrode is x0, 0, and this is negative x0 and 0. So what we're calculating is the voltage between this point and this point, plus this point and this point.
Okay, I got it. So as you do the different kind of solid, different kind of like KCl and NaCl, so have you controlled the concentrate of the two, like to make it the same concentrate?
Concentration?
Concentration, yes.
Yes.
So you think that will affect, concentration will also affect the result, right?
Yes, because the ions inside the liquid is different.
Okay.
The concentration of the ions will be different. That's what I mean.
Okay, so that's maybe all of my discussion.
Thank you. That's a great discussion.
Thank you.
1 minute for the opponent to summarize this work.
Okay, so as I just asked, why? So as I just asked, they have tried to control the concentration of the different liquid, and they believe that the different concentrate will also affect the result, and which they will improve it in the future. And also they think that different temperature will not affect that much, and they think they control their experiment time in about 10 minutes. So there will be less electrolysis and maybe some ion affecting the result. So this is my overall summary.
3 minutes for the reviewer to ask questions.
For the opponents, I want to ask, you mentioned the question about how long did the time of the experiment last?
Yes.
Is that correct?
Yes.
What was your purpose of asking this question?
Because it will affect, when the time takes longer, the water will electrolysis.
So you mean it might affect the final result of
yes,
your
of course, I think.
Yes, okay. Okay, you also asked a question about the position of placing the detecting needles, right? And what was your purpose of asking?
No, I'm just understanding the experimental setup.
Understanding the setup.
Yes.
Okay, thank you. And okay, for the reporter, I want to ask if, because we put the electrodes in the water for, you said 10 minutes for your experiment, right? So I want to ask if there's ruins on your electrodes, because that might affect the experiment, right? Rust, sorry. Rust.
Can you rephrase that?
Rust. I mean, if you put rust.
Yes, that is a possibility. So for each experiment, we change the weight that we served as the electrode, so that the problem you stated will not cause a difference, and we mitigate the influence of the possibility.
Okay. And oh yeah. Did you for the reporter, did you detect the electric movement?
The electric movement?
The electric movement. Did you detect the electrical qualities of the phenomenon?
Can you rephrase what you have said?
Did you detect different dielectrical qualities in your phenomenon?
Dielectrical qualities? No, we did not, and that might be an improvement for our experiment.
Yes, because in our experiment we detected some different the movement of the electrodes when we use different solute. So that may be a improvement, I guess.
Okay, I'll try it in the future.
Thank you. For opponents, you mentioned a question about the temperature. Is that correct? So what was the purpose? What would you want to know about?
I want to know about the correlation between the temperature and the resistance.
The position?
Resistance.
Oh, resistance
and
between
the liquid, because sometimes the liquid will be affected by the temperature.
So, and the reporter responds you as the temperature may not affect the final result. Is that correct?
Yes.
Okay, time's up.
Thank you.
Thank you.
2 minutes preparation time for the reviewer. Hey, if you please take the floor, you have 4 minutes to present.
Okay, honorable judges and opponent, this is our review throughout the whole session. Okay, this is a problem statement. I believe you guys are all clear to this, so I'll just skip this part. So for the reporters, your pros and cons that you propose pros are careful experiments and some clear explanations and a clear experience. For your cons, I believe there's way too much work on your PPTs and not enough experiment of different concentrations, and forget a unit in one page of your presentation. For the opponent, your pros are you pointed out a lot of less of reporters' experiment, and you pointed out a lot of variables in their experiment that can be improved. For the cons is that you're on clear purpose of asking a lot of questions and not involve further discussion with the reporter. What they discuss questions like they ask about what position did they put the detector, and the reporter answered in the bottom. There's no further discussion, as I mentioned. So, and they also ask about will the different concentration of KCl and NaCl affect experiment, and the reporter responded they did not try different concentrations. As I mentioned, this may cause a lack of experiment. For the opponent's question, how long did your time of experiment lasted? The response of the reporter answered 10 minutes. And also opponent asked, is there bubbles in the experiment? And the response of the reporter is rarely bubbles because the detecting needle is put in under the water. And the reviewer believes that we don't know the purpose of this question. Also they asked about why this different voltage in the water doesn't have closed loop of equipotential lines. So they answered it's because those ions may exist in the tap water. And also they asked about why didn't they try the distilled water, and it is because that distilled water it's non-conductive, so it cannot be used in this experiment. I believe this is a small mistake made by the opponent. Okay, also about the temperature, we are not sure the reporter didn't show us enough proof about that the temperature will not affect the final result of this experiment. So I believe there's maybe further discussion can be made. Okay, and also they ask about the purpose of choosing the solute, and the response of the reporters is that so that they can control the movement of ions. They choose KCl and NaCl. Is that correct? KCl and NaCl.
That's true.
Yeah. I want to ask if they have time to answer me. Did they consider other different type of solute to not just KCl and NaCl? Okay. So we got a question for the reporter. Do you think if there are multi-electrodes, will the equipotential lines be the same as your result to your experiment? This is our question. And I believe that is all. Thank you.
Okay, concluding remarks for the reporter, 2 minutes.
Honorable judges and worthy opponents, and now I'll start my concluding remarks and some explanation of our experiment. So first, the concentration of the saturated solution will change over the time, so the time span will not cause a great difference in our result. And second, different kinds of electrolyte will lead to different shapes of equipotential lines. And third, the temperature may influence the result. This is to explain why we make the same temperature every time and do not change the temperature. Because if we change the temperature, the solubility of the solid, like NaCl, will differ and causing different concentration. So that will influence the result and have many different parameters at the same time, so we make sure the temperature is the same. And the next one, the solubility of the sodium chloride won't change because of the temperature, and that's a characteristic of sodium chloride. So one of the questions is if the temperature will change, and for the sodium chloride, it will not change. And the last one is our improvement. And our improvement is that we can do more parameters, including different concentration of the liquid. And also, there's some questions from the reviewer, and he said that it will be different when we have a lot of electrodes inside the liquid, and we think that it will be, because if there's a voltage difference and we can detect the difference of the electrode equipotential lines, and if there's more, then they will have some interaction between each electrodes. So that's the reason.
Okay, time's up. George, please ask questions. Do you have any?
Please turn to the equation page. Equation. Yeah, here. Okay. The first equation about electrical field. Can you explain?
This is the formula for electric field, and here are some values for it. For example, the absolute the R here means the distance from the two points that we detect, and the lambda here means the linear charges density, and also consider the permittivity of the liquid, which will be different when we use different liquid and different solutes.
So suppose we change the geometry of the electric field, the electric will change, right?
I think it will.
Okay. And that's the next equation. Why the potential need to accuracy with negative? Why we add the negative term to E?
Firstly, that's the definition between the electric voltage and the electric field, and we believe that might be because of the direction, so that we have to add the negative.
Okay, good. Okay, good. And next page. Next. Okay, good. And here, if the positive charge, or positive electron, you lose 3 voltage, right? Okay.
Yes.
And now you have the multimeter.
Yes.
Okay. Can you show me or tell me how to use the multimeter? Turning, how to turn, and the position you measure in this page. Simulation, just simulation. Okay.
Simulation?
Yeah.
Okay. So first we have to turn to the, there are different points, and I will turn to the voltage, which is corresponds, which is the best for the measurement in this condition. And then the place we plug the two probe is we plug one point here, and another point
Where?
on the electrode.
On the electrode.
Yeah,
Okay.
and okay. And
How do they have 2 sides? One black, one right, right? So you should put it here. You should point it here.
So you have 2 electrodes. One you put on the
Yeah.
negative electrode. How about
You
the
have
other
2
one?
probes, right?
Yep.
In multimeter, you have 2 probes.
Yes.
Okay. You should point where?
In our experiment, we'll put one on the electrode and another on the different points in the liquid to detect.
Liquid where?
We have a graph paper that draw lines, and on the points that we mark, and we measure the voltage at the point. By this way.
Okay, so black player. Plate player.
Can I seek advice for this question from a teammate?
No. Okay, just you. So this experiment that you do, right? But suppose the
do it as
your teamwork.
Yes, that's
it's
our
okay.
teamwork. So
You can explain.
okay.
Yeah.
It's the different potential difference, so should be difference, right? So what's the 0 point? So I think you
Where is
mentioned
point?
that's the different potential difference, right? So you should be two voltage, right? So what's the 0 points? Or what's the 2 points? Where is the difference of the position of the point?
Yeah.
Okay.
Okay, so so in the experiment we can if we use the gap between the two voltage, for example, in our experiment we use 6 volts, and here will be positive 3, and here will be negative 3. And this is not the definition of the electric voltage, so we add a correction in our formula, which is the 5/2. So in this experiment, 6/2 is 3, so we add 3 to each point. So here will be 0 and here will be 6. So that will be will fit the definition of the electric voltage.
Any other questions? You mentioned the thickness of your liquid. The height.
Okay.
You said it has to be very shallow.
Yeah.
Why is that?
Because if we have a really thick, really tall water, I think there might be 3-dimensional equipotential lines that may cause a difference. So we make sure the water is shallow enough so that we can maybe mitigate the 3D.
You to agree with reporter's answer?
I'm quite agree on it.
Yeah.
Because
Okay. Any other questions? No? Okay, thank you.
Thank you. And I think that's a great discussion. What I'd like from this discussion for the equipotential lines, and I'll improve for the different parameters.
Okay, scores for the reporter. 8, 7, 8, 8, and 7. For the opponent, 6, 6, 6, 7, and 6. For the reviewer, 7, 6, 7, 8, and 7. Okay. A reminder for each team, please prepare your graph when you prepare your work. Okay. Don't wait until the time starts. Then you turn on the transparency. Okay. You can put a piece of paper on the transparent on the view graph. Okay, you just put a piece of paper, drag the view, and that will save you some time. Okay, now we have to take a break. 10 seconds. Okay, change your seats before leave.
没有做实验吗？
因为他们每次是不满意的。
昨天没有多学，有啊，
我们第二个被 reject， 没关系，下不对，我选到最后。
我觉得教练说比较好讨论。那个桥啊，我后面听我都不太能自由点。好，跟你讲。
我等一下进去化学应该是
你要撑10分钟。看你不是很会撑。这是我们的还是这种？没事嘛，我去买一次。不是的，太贵了。
我们第一次调，太强。你知道我在review的时候没有第一次调，没有报单，然后最后自己打。哎呀，你们帮我，你们没有人帮我，你们的经理过来发呆。对。超难的，我们超烂的，我讲超烂的。你们在讲哪？叫我来看他自己那个给我。
他用你认识，
根本在借鉴。他没有借鉴，我就没有做实验。他那个图是网上抓的。下次你要不然你要加油。
其实有2种方法，一种是电流，2种是电流。就是假设你这边点，然后不好意思，我要走了。
要有一个大学
实验室分批做，对，大学是要多用。那有没有看到这些电影？
就是这个中如果没有自由电的话，它会导致其实一通电会让那个里面的理它不是理没办法。
那你那个，因为你们时间差不多，如果继续，你们打电话发现你的，哦，这是我的手机。
等一下给
就你这样测一下，就会发现它后来那个一个整个来回开出来拉，整个会开出来。就是你如果有这个理论，我们把时间做出来。对。
这个我会发现，因为我们的手是用
差不多3分钟左右他就开始跑，所以我就只能做3分钟的写，然后再等他，就开始就会散开，然后再写，总共界定，然后再做别的。我那时候就是跑到我的在看手，我只会问我那个知道我在看手，跑到60一点点。
我以为这是谁最简单的？
后来发现有出事，
然后我发现我完全不好意思，你知道我们
1月才6月。
然后呢，他开学的时候还开始，你可以看到他过年。
那我过年有事情。
前面都是我的这些实验。所以说你刚刚讲的他靠英文，是英文，我感觉是。换鞋子没差嘛？就先接起来。
是我还因为几天他们。
哦。
那你们说现在有的那个会防地震会爆的？
没有，我们这题没有做。但是我刚没有。你们在现有没有防？就是你们正负6。
他跟我讲到，我9月要帮他去讲，因为我看。
就是有怪吧，画出来的，就是那个图形在旁边那个。
好了，你要说。你要说。
我用夜晚。
专读化。
好，你是要放那一次，
所以你个人的。
我也给他，尽量的精准，报他的那个，先报他，
尽量。因为我
饥饿游戏的。
真的我有空哦。好，没有是他很胖。现在真的是王没人太胖，你要留在，你要留在那些有钱人的。
通通都是你学的。然后我发给你最后的。哇。但是我是开起来他说你就不要那个，于是他们就被淘汰。有遇到你就说原来他们应该是觉得喜气快，
咱们等一下加油。你要把简报先开，简报先开，我等下做一个，再开始再点。
坐在那。
开电视节目的时候讲这个政论，讲一堆，我看每台都是讲电啊。
讲了吧，就缺电了。
你们缺电缺了多久啊？
停电停多久？
停多久？
高雄2个小时啊。
不止吧？
没有，这2个小时就来了，我们那边
我们说回来之后就。
现在是最小时啊，就总共最小时，就2个小时。
没有，我家那边。
家里没事，家里好 像就是
1秒，
就是断掉。
在那边地下会长。
缺电哦，缺电。总统应该去连，先生不缺电，总统就去那边哦。总统就
大理寺就有发现，对，是那边
你说台北缺的，
他们迷路了好多。
我都没有碰到。我刚离开学校，我们学校就缺，可是我刚离开家里的票，所以我都知道。
多久？
家里大概是省一下，学校大概也是省一下，因为学校可能会有外交或是去 KT。
对，老师，我昨天其实想过一个蛮这个问题，让我觉得太白烂了，就被骂。我老师在做带停电话，大概停电的话怎么办？
我们假设他不会。
因为没辙啊，我觉得这个停电也没辙了吧？
那个很乱，
是这样吗？
说下礼拜新调300，所以下礼拜可能会再调。怎样？你说老师也有打，不用打，就是这样子，打电话，苏联那天就在打那个。
去我们去被要求降档，然后那个就是
他是跳脚。
他不能跳脚。
他跟家长。
我说谣传出来，他们被迫这样子，谣传。
那他就说那我就没有东西卖，你睡。
然后就把订单往后延1天2天呢。
那1天2天护国神山，对护国神山。
就像我们说，我们跟人家签约天然气会长，人家如果不交货，我们没办法，对不对？
啊，是啊，没错。
罚他违约金。
Okay, I suppose everybody is here now, right?
Yeah.
Okay. So we start our last session. Okay. So the opponent, please pose your question for the reporter.
Oh, that's great.
I'm sorry. Please go ahead.
Number 14.
Number 14.
Yes, sir.
Accept. All right. So we'll debate number 14. Problem number 14. Please write down your names on the blackboard for each team presenters. You may start early if you want.
So, honored judges and fellow competitors, I will be presenting problem 14 on ball membrane heating cost. And here's the overview of my presentation. We will start with the introduction, which is the problem statement, and theoretical model, including qualitative explanation, quantitative models, and doing experiments, and discuss the relevant parameter, and conclude with a conclusion. So here's the problem statement. When dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. So here's the demonstration. Sorry for the technical error that we record the sound but the computer can't produce it. So the statement continues. Explain the origin of this sound and explore how its characteristics depend on relevant parameters. So we will focus 2 points on this presentation. The first one is how will the sound be generated? And the second one is how will the relevant parameter affect the sound? So we believe that when we drop a metal ball on a rubber membrane will cause a vibrating rubber membrane, and which the membrane will cause movement in surrounding air molecules, and which the sound described in the statement can be heard. So because of that, we consider it the acoustic resonance in closed pipe. And why is the plastic cup a closed pipe? Is because here's the rubber membrane and here is the plastic cup, and so here's the sound where the sound is generated, and so the other one is the bottom of the plastic cup, then it is closed. So we consider it a closed pipes. And the relationship between the pipe length L and wavelength is described as the wavelength is equal to 4 times pipe length over N, and the N represent the odd numbers. And the relationship between the frequency and the pipe length can be described in N times the velocity of the sound and over 4 times the pipe length. And the N is also represented as the odd numbers. And the L is the distance between the rubber membrane and the height. So this is our experimental setup. So metal ball and rubber membrane and plastic cup is required in the problem statement. And because we want to consider the parameter of the pipe depth, so we need to control the release height of the metal ball. So we use the ruler to control the release height, and we use microphone to record the sound. And so, as I just said, we want to investigate how the pipe depth will affect the sound, the frequency. So by adding the water into the plastic cup, it will change the pipe depth I described before. Then we drop the metal ball on the same height, and the initial of the drop position on the membrane is also be controlled. And then we record the sound. Then we use the audacity to analyze our sound. And so first when we get our sound record, then we use the noise reduction to get rid of the noise. Then we use the spectrum analysis to find the highest peak, and we consider the highest peak of the bass tone. And that is the frequency we consider in the following chart. So here's our result. As you can see, the X is the pipe length and the unit is centimeters, and the frequency is in the 1,000 hertz of the unit. And obviously, when the pipe length is getting longer, the frequency will get slower. So which means that the pipe length and frequency has a negative correlation in it. So here's our discussion and conclusion. So as our qualitative explanation, the sound is generated from the resonance of air molecules in the plastic cup caused by the vibrating rubber membrane. And as I just said before, our theoretical model consider the N represent the odd number, and the permutation of the frequency we measured also exists in the trend of odd numbers. And the frequency of the base tone is negatively correlated with the Python just described in the chart. But however, and now we think that the statement requires for the investigation of the vibrating membrane, because the statement asks us to explore the origin of the sound and instead of our investigation of the resonance. And I think that is my presentation.
Okay, opponent, you have 2 minutes to ask questions.
Okay, so I'd like to ask, how can you ensure that the sound you measure is from membrane, not echo or something else?
So, due to my knowledge, I believe that when the distance between the microphone and the membrane is larger than 17 meters, the echo will be heard. But in our experimental setup, our distance is grades lower than the 17 meters, so there won't be the echo recording the sound.
And how can you ensure that the tension won't change during the experiment? I mean, membrane.
So I forgot to mention that because doing the experiment, we believe that when we change the tension, it might change the frequency. So in order to control the tension of the membrane, first we make the rubber membrane stretch over the plastic cup, then we use a pen to draw the circle, the boundary of the plastic cup. Then we add water in it, then we put the rubber membrane over again and make the boundary we just draw before also matches the boundary of the plastic cup.
Okay. Oh, that's all my question.
3 minutes preparation time for the opponent. next now 4 minutes for the opponent to address this question, the total 40 minutes.
Okay, so I'm the opponent from Team Sound, and these are the problem statement I will state, and these are the main focus, explain the origin of the sound and how its characteristics can depend on relevant parameters. And these are the phenomena that report it says this phenomenon is the sound and vibration of the membrane, and theories in energy and simple harmonic motion, and then experiment is mass of the ball, height of the ball, and total energy and characteristic of the membrane. And these are the pros and cons of the reporter. They clearly answer all the questions of the problem statement, and they clearly mention the relevant parameters. And they use a chaotic resonance to explain the theory in the experiment. And the con is they didn't clearly mention how they get rid of the noise, and they don't have enough data to explain their experiment. And these are points to be discussed. The frequency of the echo might be similar, so the sound measured might be the echo as I say in the 2 minutes question. And how can you know that frequency is not the same? Is not because of the decreasing height of the ball, but the different dropping position of the membrane. I mean the ball is lower and lower. Yeah. It was decreasing, not because of the lower and lower, but the different position dropping up at the different position. And how do you keep the height accurate of your initial speed? And have you tried other material of the menu? And I like to ask in the discuss, that is, how can you ensure that tension will? Oh, sorry, I repeated it. I skipped that. What if there's angle at the surface? What do you think, how will it affect the experiment? And what do you think, what part will the mass of the ball affect? And what do you think, what part will the tension of membrane affect? And how much layer of electric stuff do you use for the membrane? And that's all my presentation. Thanks.
Move to the discussion.
Okay, so have you tried our material of the membrane?
Yes, we tried, and the different type of the membrane is, we call it condom. But we didn't use it because when we are doing the experiment, we found that the condom, the membrane is too easily to rebound. So which means that the sound cannot be constant. So yes, so we decided not to use that, and then we used the gloves for the rubber membrane.
And what is their angle at the table, at the surface? I mean.
Do you mean?
What will the phenomenon be if there's angle at the surface?
Do you mean that my assumption not be considered?
Yeah.
So I think if there's an angle between the plastic cup and the table, there will consume the energy.
There will consume the energy.
Yes. To the ball.
I'd like to ask the question of how can you know that frequency is not the same? It's not because of the decreasing height of the ball, but the different dropping position of the membrane.
As I just stated before, our measurement method is control the release height and the dropping position of the membrane. So we can certainly know that it's not influenced by the position.
Okay. So where did you drop the ball at the middle of the slide?
In the middle.
In the middle.
The position is middle of the membrane.
You draw the middle of the membrane.
Yes. To supplement that is because we believe when we stretch over the plastic cup, the tension the surface tension that is on the rubber membrane isn't distributed evenly. So, and we consider that the center of the rubber membrane is the most even one of the tension.
And can you show me your video of your experiment? But they bounce it on the side, but it might affect the tension of the membrane.
But we did the experiment. We choose the position in the middle. So this is the demonstration, not the experiment.
But it might bounce at the edge.
Yes, it might. So when we record the sound, we choose the bass tone of the sound. And if we also observe the recording of the sound. So if we know that there's a sound produced by when the ball is dropped on the edge of the plastic cup, we will deduct that part from the recording.
So as you say at the question sign, you say you have enough height to remove the echo sound, right?
Yes, because our distance between the membrane and the microphone is great smaller than the 17 meters. Because the restriction of the forming a echo is bigger. The distance is bigger than 17 meters. So we believe that there's no echo in the
so small to record.
I would like to state what I just said again. So we know that when the distance is bigger than 70 meters, the echo sound can be clearly heard. But when the distance is totally equal to the 17 meters, then the sound and the origin sound and the echo would just match totally. So we can hear it, but in our experimental setup, our distance is really lower than 70 meters. So we believe we don't need to consider that factors.
Okay. Then how about your background sound?
So as I just presented before, for the noise reduction, after recording the sound of the sound, then we will record a background. So we record two parts.
So you just separate it?
Yes, separate recording. And after we got this two recording, we will give the density a sample of what is the background noise. Then we gave the sample of that, and we use noise reduction to reduce the noise.
decided to choose acoustic resonance to explain the theory. And why not explain the theory by energy transformation?
Because we believe that when the rubber membrane vibrates, it will cause a movement in surrounding air molecules, and the surrounding molecules will transfer the sound waves to our ears, and we can hear it.
But you can still model in using energy.
But we believe that there will exist some energy decay in the real model that we can't really control it.
You can't really control the energy that decays that.
Because we believe there will have some energy decay that we certainly can control it. So we don't consider the energy models.
Okay, that's all.
Okay. 1 minute for the opponent to conclude the discussion.
And as the reporter said that he used higher than centimeter to depart from the echo sound, and that's part of very good job. And he considered the echo sound, and yes. He explained the theory in detail, and he even separated the background sound with the sound that is going to be recorded.
Okay. You will have 3 minutes to ask questions.
Honorable judges and worthy opponents, I'm the reviewer of problem 14, bond membrane. And my first discussion is for the reporter. Did you consider energy transformation during the process?
No, we didn't consider it.
How about the opponent? Did you think that the energy transfer? Can you tell me what may be the energy transformation?
And when you drop ball on a height,
yeah,
and you have potential energy to drop, and it will transfer to electric energy, and it will bounce off and cause the air vibrating to make a sound.
But did you agree with what the opponent said?
I agree with what the opponent said, but I would like to add some more information to it. So, apart from the potential energy, and there would also be the energy of the heat, and caused by the when the ball drop on the membrane, it will have friction.
Okay, thank you. This next question is for the reporter also. If you use your hand to drop the ball will spin. How can you make sure that the spinning of the ball will not affect the result?
We didn't spin the ball. What do you mean by drop the ball?
It's just when you drop the ball will spin.
Actually, how we drop the ball is just imagine this is a ball.
Because there will be friction on your hand. you will give a friction to the ball. When you drop the ball.
So we drop the ball like this. So we consider it the free, like free body. Free body.
So, okay, thank you. How about, again, for the reporter, did you consider different shapes of the membrane, like a circular one or a square one? Did you consider? How about the opponent? Did you think that the shape of the membrane will affect the result?
It will affect the result, but yes, it will, the elastic coefficient will change.
Okay, thank you. For the reporter, did you consider different tension of the membrane?
We didn't do the experiment of the relationship between the tension and the frequency, but we have considered it.
Okay. Let's
Thank you.
so the time we have now 2 minutes preparation time for the reviewer. Okay, 4 minutes for the reviewer to present his thoughts.
Honorable judges and worthy opponents, I'm the reviewer of problem 14, ball membrane. And now, I'll first talk about the main focus of the reporter. The first focus is how will the sound be generated, and their second focus is how will the relevant parameters affect the sound. And now, first talk about what the reporter said. First is the phenomenon. It's when a metal ball drops on a stretched rubber membrane, a sound will be heard. And then it's the theory. They talk about the acoustic resonance in closed pipes by analyzing its frequency and the relationship between the cup's length and wavelength. And as for the experiment, the reporters said that they dropped the balls on the membrane by hand, and they used ruler to measure the height and the microphones to measure the sound. And now I'll talk about the pros and cons of the reporter. First, for the reporter's advantage, they identified the correct key questions of the problem. Second, they analyzed 5 different parameters. Third, they use clear pictures to demonstrate their experiment setup. Fourth, they use scatter plots to demonstrate the result. As for the disadvantage, they failed to analyze the deviation in their data. Second, they lack concrete evidence to support the theory. Third, they lack the they lack different parameters like the tension, membrane's material, and further they lack supports of the conclusion, and last, they don't have enough explanation for the outside factors. And the opponent presentation it talks about the pros and cons about the reporter and the structures and questions to the reporter. And the advantages of the opponent is first, conclude reporter's presentation precisely. And second, he brought out several questions about the theory and experiment. As for its disadvantage, first, he asked some confusing and irrelevant questions. Second, they failed to lead to further discussion. And last, they asked questions that the reporter had stated previously. Now I'll talk about the discussions between the reporter and the opponent. First, the opponent asks, is there enough height to remove the echo? And the response of the reporter is, yes, the height is far smaller than 70 centimeters, so there is no echo. And I believe that the echoes should not be a considerable error in the distance. And next, the opponent asks, will the location where the ball drops on the membrane affect the result? And the reporter answer is, if the ball drops on the edge, the reporter will reconduct the experiment. And my personal opinion is the different locations of the ball cause different modes of vibration, leading to different frequency. And next, the opponent asks how to remove the background noise. And the reporter answer is, they use noise reduction to reduce the noise. And I agree with what the reporter said. And for the opponent asks, where did the reporter drop the metal ball? And the reporter answer is, at the center of the rubber membrane. And my opinion is the place will influence the results. And the next is, I asked, did you consider energy transformation during the process? The reporter answer is no, they didn't consider, but they agree with the opponent. And the opponent answer is the potential energy transforms into elastic energy and cause the air vibrating, which will cause the sound to be heard. And their point is first, they miss some parameters, like the different shape of the membrane, different tension, different material of the membrane, the different height of the air column, and different mass of the ball. And they missed the calculation for resonance on page 5, and they didn't consider the spinning of the ball when dropping the ball by hand, and then the vibration modes of the membrane, they didn't discuss about this. And this is the end of my presentation. Thank you.
Okay. Concluding remarks by the reporter, 2 minutes.
So I would like to clarify that the distance between the membrane and the bottom, the membrane and the bottom and the microphone is less than 17 meters, and the echo will not be that apparent. And we control the tension by drawing same size of the circle on the membrane, and to supplement that, we change with the same membrane and draw the same size of the circle to prevent elastic blockage. And we have tried other materials of membrane like conduit. And ball falling on the edge will affect the result, so we will reduce the part of the noise from the audacity. And we reduce the environment noise by using audacity and recording background noise. And we believe that releasing the ball with both fingers at the same time won't cause friction. So we don't need to consider the spinning of the ball when we release it. And the shape of the membrane won't affect our result because we drop the ball at the center of the surface. And that's my concluding remark.
Okay. Jury, please ask the questions for the team. Any questions?
A quick one, question. How about the sensor? The detection of the sound position will affect the result.
I believe it will influence.
Yeah, I agree with what the proposed. Yeah, I agree.
Could you turn to page 8? Your experimental data. Yes, how many times did you do the experiment for each point?
What?
how many times did you do the experiment for each point?
3 times.
3 times. You take the average.
And we calculate.
What's the range of your average? What's the range of your data? Because from the view, from that the data,
we didn't calculate the error bar.
Okay. Okay. Could you turn to the previous page? Yes. On the left-hand side, you said you determine the frequency according to the maximum peak. Why is that? Why didn't you take the very first point, very first peak as your data point?
Because we believe that this peak is the noise from the caused by the microphone.
Your noise?
Yes.
You already reduced the noise reflection.
Okay. Did you study the bouncing of the balls generating the sound as a whole range, not just the very first, whatever the maximum peak?
The whole process.
The
not
whole
just
process. Did you consider that? Can you explain that?
Can you explain it again?
The whole process.
So we drop the ball. First we.
As time goes by, you measure the whole frequency change. That's it.
Yes. We measure the whole frequency change.
What did you see? Can you explain that?
So when the frequency change,
Did you see a frequency change as time goes by?
yes, we see it.
Why didn't you discuss it?
Because based on our theory, we want to know that how the Python will affect the frequency.
You two have any?
I can answer. I think because there are many frequencies, right? And so I think because the different vibration of membranes follow Basel function, and so that there are different modes, and which leads to different frequencies.
Why there's different modes?
If we use, if we observe the.
Okay, let me rephrase my question. As you did the experiment, you observed the increase of frequency, right? You agree? The frequency increases of the sound. You hear the tone of the sound increase.
Yes.
Why is that?
Because the rebouncing of the metal ball on the rubber membrane will getting lower and lower.
Why is that?
We think that's the energy decay, the energy transfer.
Why is the energy decaying? The two
There's
any
because we believe that the surface tension that is unevenly distributed on the rubber membrane will cause the energy decay.
You two agree?
I think no. I think sound is only related to the membrane vibration. I think it's only related to the material and the tension of the membrane.
Okay, I think our time is pretty much finished. Right. Thank you very much.
Thank you.
Okay, let's show the scores for the reporter. Five, 6, 6, 7, and 5. Opponent. 5, 5, 6, 6, and 6. And the reviewer. 8, 7, 8, 8, 7. Okay, that concludes our session. Thank you everybody for taking part.